So the last topic under the sun for us in Calc 2, at least in this course this semester, is we're going to talk about the length of a curve in parametric equations, okay? So it says, development says it uses the slope of the tangent formula, which it does. So let's go back to this and say, x is some sort of function of t. These are parametric equations, okay? And what we'll do is we'll go straight to the length of curve formula that we've already developed. So if you've got y is some sort of function of x, got a curve running through space, and you want to know how long it is from point A to point B, let's say, okay, we have a formula. It's the length is integral from A to B, right, of the square root of 1 plus dy dx quantity squared dx. And that's what we're going to use. We're going to use that guy. We'll say recall from, I don't know, rectangular, no, let's call it from previous section. The length of curve, as I described on the side there, is the integral from A to B, square root, etc. Now that's an integral with respect to x. Trouble is, our functions are both functions of the parameter t. How do I make a bridge from one to the other? And as I hinted at up here in the development, the bridge is right there. We have a formula for that guy, so let's put it in. So it's equal to the integral from A to B, square root, oh, I don't have any room, of 1 plus, in here I'm going to write in red, dy dt divided by dx dt squared dx. The next step here is to factor out the dx dt downstairs. So I might write this in a weird way. I'm going to write it as, let's see, yeah, common denominator maybe. Integral a to b, big old square root, make it tall. It's going to be dy dt quantity squared, and then the 1 I'm going to write it as dx, and let me make some room here. Okay, so it's going to, let me write it again. It's going to be dx dt squared plus dy dt squared over dx dt squared dx. Okay, so what happens is I'm going to square root the denominator and invert and multiply with it. And it looks like this. Okay, we have a square root. We have dx dt squared plus dy dt, quantity squared. And I have square rooted dx dt downstairs, but it becomes dt dx, and it meets dx. So here comes your formula. The formula is simply the length of curve for parametric equations is the integral from, I don't know, whatever the limits are for t, where 0, oh, no, not 0, but let's say c is less than or equal to t is less than or equal to d. So integrate from c to d, and instead of 1 plus, it's dx dt squared plus dy dt squared. And that's your formula. Okay, so now we have another length of curve formula. We have one up here, and there's another one right here. There's going to be a third one with polar, by the way, polar coordinates, which is coming up next video. So let's do this problem that got kind of crowded in here. Show you how this is done. It's not going to be anything too majorly earth-shaking. We're simply going to do a length of curve. So it says find the exact length of the parametric curve. Let's write it again. X is e to the t minus t, and y is, I can't read that. That's what I thought. Is 4e to the t over 2 And we're going 0 less than or equal to t less than or equal to 2. So I'm going to show you how to do this problem, length of curve, okay? Okay. All right. So what we need is dx dt. Did you notice that in the formula? And also dy dt. Okay, have at it. I'll wait for you. All right, so this guy is e to the t and then minus 1, isn't it? Okay, and the other one is equal to, it's going to be 4 times e to the t over 2, but then you derive 1/2 t and you get 1/2. So upon cleaning that up, what we have really is 2e to the t over 2, 2e to the t over 2 power. We need those derivatives because here comes the formula. The length of curve is the integral from what to what? Look at that, I put it so close together. From 0 to 2, correct. 0 to 2, square root. Now I'm going to put, let's see, put this in red. I'm going to put the dx dt, e to the t minus 1 square plus the square of this other guy, which is 2e to the t over 2. 2e to the t over 2. Success in this particular problem is being good at algebra, pretty much. Can I do this problem algebraically? Let's see what happens. So I got a little room over here, so let's see when we square that stuff. The whole goal, if you remember, is can I get out of that radical somehow? I hope. So we're going to get e to the, now here's the thing, I got to remind you, e to the t times e to the t again is e to the 2t. You add up the powers. So when you square it, or you can think of it as e to the t squared, you multiply t times 2. So you end up with e to the 2t there, and then you multiply, you get minus e to the t, but then you double, so it's minus 2 e to the t. And then lastly, plus 1. It looks like plus 1 right there. Now the next one, we square that, we got a plus 4, and here we go. E to the t over 2 times e to the t over 2 becomes what? It's 1/2, and 1/2 is 1 whole t. So that does become e to the t dt. Now I wanted to show you that because one little mistake and we're sunk, right? So what are we ending up with? Let's see. We've got the length is integral from 0 to 2. We've got the square root of this thing. Oh, this is looking pretty nasty. So we have e to the 2t, okay. Then we have 4e to the t minus 2e to the t is plus 2e to the t, and then plus 1. This guy is clever. He must have gotten this out of a magazine. I have a lot of experience with this. I was wondering, do I know how to do this one? But I do, because what I see in there, in that radical, is a quadratic form. In fact, people can, from Algebra 2 days, if you let u equal e to the t, then you're looking at something that looks like, and I'll put it over here, it's u squared plus 2u plus 1. Okay, I'm going to keep it as dt because I'm remembering that this is what I substituted. All right, so we've got integral 0 to 2, square root, guess what this is? It's u plus 1 squared dt. Really what this is, 0 to 2, is the square root of e to the t plus 1 squared dt. See, it's always a trick. Somehow it's a trick to get out of that radical, but we did. That cancels, and we have now the integral 0 to 2, e to the t plus 1 legit. Okay, integrate, e to the t plus t. Apply the limits, 0 to 2, e squared plus 2 minus e to the 0 minus 0, and we're getting e to the e squared plus 2 minus 1, or e squared plus 1. The actual length of that curve is e squared plus 1. Okay, so yeah, shenanigans with algebra to get that one done. And that's it for section 2. You just have to practice it. Yeah, be sure that you're able to find those tangents and all that kind of good stuff. All right, See you in Polar.